Hi everyone. Today we'll learn 4 different ways in which we can denote the derivative. Let's start by reviewing a few simple derivative formulas. If you would like to try this exercise on your own first, download these notes using the link in the video description. I believe that the derivative of the first function is 3, and that is because the function is a linear function, so its slope is its derivative. The slope is 3, so the derivative is 3. We found the derivative formulas for the remaining 3 functions in one of the previous videos. If you haven't watched that video, I will add a link in the video description. We used the limit definition of the derivative to show that the derivative of x squared is 2x. We also used the limit definition of the derivative to show that the derivative of square root of x is 1 over 2 square root of x. And finally, we used the limit definition of the derivative to show that the derivative of 1 over x is negative 1 over x squared. I used the prime notation to denote these derivatives. There are at least 3 different ways in which you can denote the derivative. The prime notation is often called Lagrange's notation. Given the function f, you can denote the derivative by f prime. And if you want to specify the variable, you can write it as f prime of x. Newton's notation is similar. To denote the derivative of f, you put a dot above f. If you want to specify the variable, you say f dot of x. Euler's notation looks like the following: df derivative of f. If you want to denote the variable, you could say df of x or df of x. Fun fact is that even though most people call this type of notation Euler's notation, there is no evidence that Euler actually used that notation. Finally, Leibniz notation is the following: the derivative of f with respect to x, or the derivative with respect to x of f. If you want to specify that you are taking the derivative at a particular point, this is how you do it. For example, if you want to specify that you take the derivative at x equal to 2, and you want to use Lagrange's notation, you would say f prime of 2. If you wanted to use Newton's notation, you would say f dot of 2. If you wanted to use Euler's notation, you would say df of 2. And if you wanted to use Leibniz notation, you would say df dx, evaluated at x equal to 2. In calculus, we often use Lagrange's notation and Leibniz notation. In physics and engineering, people often use Newton's notation. And in higher level mathematics classes, people use Euler's notation. We will practice all 4 of them, but we will focus on Lagrange's notation and Leibniz notation in the future. If you would like to try the next problem on your own, stop the video now. We must first compute the derivative of f, where f is given by this function. Because it's a linear function, I know that the derivative is the slope, which in our case is 4. For part b, I'm given Lagrange's notation. I must find the derivative of f, where the variable is s, of the function 1 over s. We know that the derivative of that is negative 1 over s squared, which we know from the first exercise today. In part c, we are given Leibniz notation, the derivative of g of t, where g of t is given by t squared. I know the derivative of t squared. It must be 2t. Then Euler's notation. I have the derivative of f at the variable theta, where f of theta is given by square root of theta. This means that the derivative at theta is 1 over 2 square root of theta, using the formula from the first exercise today. In the next example, we have Leibniz notation, the derivative of f with respect to x at x equal to 9. So first, I compute the derivative of f with respect to x, and I realize that the formula was square root of x, so its derivative is 1 over 2 square root of x. And now I must compute this derivative, or evaluate this derivative, at x equal to 9. So I will plug in 9 to the formula, and I will get 1 over 2 square root of 9. Square root of 9 is 3, so I get 1 over 6. Finally, I'm given the function k, where the variable is r, and this is a linear function, and I must find the derivative of k with respect to r. So I get that the derivative of k with respect to r is the constant function 5. The derivative of a linear function is the slope of the linear function. You may be wondering where the Leibniz notation came from. Let me show you. When we defined derivatives using limits, we did the following. We chose a point. We chose a second point on the graph of the function. We denoted by a plus h. The corresponding points on the graph of the function had y coordinates, f of a and f of a plus h. Then we computed the slope of this secant line that goes through these 2 points, and we got f of a plus h minus f of a divided by h, the difference in the y values divided by the difference in the x values. Note that a plus h minus a is just h. And then we said, move the second point closer to the first. Because when we do so, the secant line resembles the tangent line more and more, which means that the slope of the secant line resembles the slope of the tangent line more and more. And to have the second point get closer and closer to the first, we let h goes to 0. We thought about h as the distance between the two x values, so as h goes to 0, the 2 points get closer and closer to each other. So we took the limit as h goes to 0. And we said that this was the derivative of f at a, and we denoted it by f prime of a. Leibniz did the same thing, but used a slightly different notation. He said, the difference in the x values of the 2 points is delta x, and the difference in the y values of the 2 points is delta y. So the slope of the secant line is given simply by delta y divided by delta x. And then he said, let's move the second point closer to the first. How can I do that? I can do it by having delta x get smaller and smaller. I can take the limit as delta x gets smaller, because as delta x gets smaller, the 2 points are closer and closer to each other. So he took the limit as delta x goes to 0. And he said, this is the derivative. And then he faced a dilemma, how to denote that derivative. And he noticed that as the second point gets closer to the first, both delta x and delta y get smaller. Take a look at the second picture. Here's delta x and here's delta y. Take a look at the third picture. Here's delta x and here's delta y. Those delta x's and delta y's get smaller and smaller. For this reason, he decided to call the derivative dy by dx. dy reminded him of a very tiny delta y, and dx reminded him of a very tiny delta x.